third talk on the session is about FlexHeap. It'll be given by Iacovos Kolokasis.
Hello, everyone. I'm going to present you FlexHeap, a dynamic I/O-aware heap resizing for managed application. Today, modern JVM systems such as Elasticsearch, Cassandra, Spark process large datasets from storage. So they require both large heaps and large I/O cache. On the one hand, large heaps reduces GC frequency. As you see in the table, from the execution of Wikipedia workload in Elasticsearch, where we have concurrent clients that perform document ingestion and query searches, in the case of a larger heap, the GC frequency is by 2 times lower compared of having larger I/O cache. On the other hand, larger I/O cache reduces I/O stalls. As you see in the table, the I/O traffic when we have larger I/O cache is by 4 times lower. As a result, partitioning available DRAM affects performance significantly. As you see, a larger heap increases the document ingestion throughput, but a larger I/O cache increases the query per second rate in search operations. So the challenge here is how much DRAM to provide for each use and how to do this dynamically to adapt to application different phases. One line of existing heap resizing mechanisms tries to reduce the GC cost to improve application performance. However, resizing only the heap for GC performance doesn't work. For example, in the previous experiments of Wikipedia workload in Elasticsearch, in this time frame, you can see we have both high GC and high I/O overhead as there are concurrent document ingestion and query searches operation. In this existing resizing policy, prioritize the heap growth to reduce the GC cost and do not consider the I/O. On the other hand, other work, they try to reduce the server memory usage by allowing more applications to run. However, when the heap pressure is high, they release little memory back to OS, and we have the same effect as with the previous resizing policy. Thus, none of the existing resizing mechanism considers the I/O cost. Today, users, to overcome this problem, they statically partition DRAM. They cap the maximum heap size, and the rest memory is used for the I/O cache. For example, Elasticsearch and Cassandra recommend to use 50% of the DRAM budget for the heap and the rest 50% for the I/O cache. However, static DRAM partitioning has 2 main problems. It's not straightforward to find the proper split and cannot adapt to dynamic application behavior. So in this work, we propose FlexHeap, a heap resizing mechanism that considers both GC and I/O cost. It dynamically resizes the heap, so the rest memory is used by the I/O cache. And FlexHeap is a resizing mechanism for G1 GC, which is the default OpenJDK garbage collector. G1 consists of 3 different collection types: young GCs, mixed GCs, full GCs, and concurrent mark cycles, where it scans the whole heap without stopping the applications to find live objects. After each GC type, we have FlexHeap that makes 2 main decisions: whether to grow or shrink the heap, and by what amount it's going to do it. Now I'm going to present you the design of FlexHeap, discussing how it decides to grow or shrink the heap, how it estimates the impact of GC and the I/O stalls, and how it decides the amount of the resizing step. FlexHeap decides to grow or shrink the heap based on the impact of the GC and I/O stalls on application performance. For this purpose, FlexHeap models the impact as a total loss potential in cycles, and also in the paper you'll find a discussion for other alternatives. FlexHeap divides execution in intervals based on GC phases, and in each interval decide to resize the heap based on loss potential. So FlexHeap, after each resizing operation, waits to see the effects, so to avoid premature actions. If we see that the total cost decreases, then FlexHeap continues in the same direction, applying the same action. Otherwise, If the total cost increases, then FlexHeap identify which is the dominant cost. FlexHeap compares the relative differences between each cost between intervals to see which cost has been increased more. Then it performs the appropriate action. So now how we estimate the overhead of the GC. GC in the G1 can be stop the world, which means that during the GC the mutator threads are stopped and they cannot run. And also we have concurrent GC phases, which means that concurrent GC thread runs alongside with mutator threads. So FlexHeap model this cost and convert it into loss potential compute cycles for mutator threads. Let's see for the stop the world GC. We interpret the stop the world GC like young GC, mixed GC, or full GCs in G1 as a loss potential from the mutators work during this pause, because all the cores are occupied by the GC threads. So we estimate this using the pause time multiplied by the minimum number of active mutator threads and CPU cores. For the concurrent GC cost is different. We count it as a cost if concurrent GC threads runs while mutator threads are waiting. For example, in this experiment we have 4 mutator threads and 2 concurrent GC threads, and we have only 4 cores. So 2 of the mutator threads are waiting, and we count this as a cost. Otherwise, if we have enough cores to run both mutators and GC thread, then we ignore this cost. Then the I/O cost now is different from GC cost for the estimation. The GC consumes CPU cores that mutators could use. In the case of the I/O, it blocks mutator threads waiting from storage to take the data, even when CPUs are busy, so creating queuing effect, which affects application latency. For example, if you see in the figure, we have, in this phase, we have one thread that's waiting for I/O, but the whole CPUs are occupied by the rest threads. Then we have 3 CPUs that are, one CPU that is idle, and because the other threads are doing I/O, and then again, all the CPUs are occupied. So we count the I/O cost as the sum of the stalled mutator CPU time. Today, Linux kernel interface do not expose per mutator I/O stall time. The I/O weight is per process level and not thread level. And also, more fundamentally, is that kernel cannot separate the I/O stall time from the scheduler delay time. So FlexHeap approximate permutator I/O stall time using eBPF on sketch switch, and we track mutator time blocked in this state, which represents that it's waiting for I/O. After FlexHeap deciding the proper action that will perform, it needs to estimate now the resizing step. The goal to FlexHeap is to shrink the heap without hurting G1 post-time goal. G1 estimates the hidden target size required to satisfy the post-time goal. And FlexHeap ensures that the shrinking step will leave enough space for the required hidden space. So we have the DRAM budget, we have the DRAM that is backed by the heap, and the rest is uncommitted. Some of this backed DRAM which is occupied by the heap is used, the rest is free. So we see how much is the hidden target, and we account for the shrinkable budget. Now, based on this shrinkable budget, we use a sigmoid function to choose how much of this budget we are going to release, and we do proportional step based on the estimated cost change. Now let's move on to the evaluation. We implement FlexHeap in OpenJDK21, and we identify workloads that exhibit continuously changing heap I/O behavior. We run Spark with Spark SQL using TPCDS workloads, Elasticsearch using ES-Rally. We use 2 main baselines, the G1 that resizes the heap to reduce the GC cost, and we use the latest version of the resizing mechanism of G1 from OpenJDK'26, and we use also VG1, which resizes the heap to reduce the memory usage. We use a server with 2 terabyte NVMe SSD, 256 gigabyte DRAM, 32 cores, and we limit DRAM capacity with zip groups. In here, we show the potential of FlexHeap that improves Elasticsearch throughput. We have the normalized throughput based on the G1 resizing policy, which we use the guidelines of Elasticsearch that says use 50% of the DRAM budget for the heap and the rest for the I/O cache. We use the VG1 and we show the FlexHeap with the third column. And we use 2 different DRAM budgets for Wikipedia, Cohere Vector, Dense Vector, and OpenAI Vector. FlexHeap improves throughput between 5 to 20% compared to G150, the ingestion throughput, and by up to 30% compared to VG1. And also FlexHeap improves the search throughput by up to 7 times compared to G150 and by up to 5 times compared to VG1. Also, we investigate how FlexHeap improves Elasticsearch latency. For the ingestion task, FlexHeap improves P99 by up to 10% compared to G150 and by up to 30% compared to VG1. And for search task, FlexHeap improves P99 by up to 25% compared to G150 and by up to 2 times compared to VG1. Here is how FlexHeap adapts to Wikipedia workloads behavior. If you see is the first run with the G1 using 90% of the DRAM budget for the heap and the 10% for I/O cache, G150 which used 50% of the heap for the 50% of the DRAM budget for the heap and the rest for the I/O cache, VG1 and FlexHeap. If you see, FlexHeap in these phases adapts better to application behavior compared to the rest resizing policy, and this is shown by the reduction by to 17% in the average I/O wait time. Next, we show how FlexHeap improves Spark SQL's performance, and we have FlexHeap versus G1 using 16 and 32 gigabyte DRAM, and versus vertical G1. In the y-axis, we show the execution time reduction percentage, and in the x-axis, we show the cumulative query fraction. We see that 43.7% and 27.2% of queries have execution time reduction more than 10% compared to G1, and compared to VG1, 30%, 26% of queries have execution time reduction more than 10%. To conclude, JVM-based search and analytics systems need more memory for both heap and I/O purposes. Partitioning memory to reduce both GC and I/O cost is a challenging problem, and existing heap resizing mechanisms do not consider I/O cost. FlexHeap partitions DRAM by estimating the loss potential from GC and the I/O stalls, and takes 2 decisions dynamically at GC phase boundaries: grow or shrink the heap, and by which amount. And we see that FlexHeap improves throughput by up to 33% and up to 50% compared to G1 and VG1. Thank you for your attention. I would like to answer your questions.
Questions?
Oh yeah, thank you for the great talk. I wonder if your methodology, your approach can be extended to other garbage collector like ZGC or Shenandoah, because I think large-scale server may use different garbage collection than G1. Yeah.
Yeah. Thank you for your question. We also think about this. Sure, we need to see there the cost of the GC. I mean, because all these are fully concurrent. We have to see how we estimate the GC cost. Maybe this methodology about the estimation, it's okay. The next thing is, whenever we're going to take decisions in these garbage collectors, which are fully concurrent, we need to see where they have stop the world phases, if they have, in order to take the decisions. So yes, it will need a bit rethinking if you're going in a different collector.
Oh yeah, thank you.
Yes.
Time for more questions. No pressure, some pressure.
So this heuristic that you mentioned which was based on essentially platform threads and what platform threads that can run to make decisions whether or not to adapt. Have you thought about virtual threads and how that's going to affect this?
Yes, no, we didn't see it with the virtual thread. It's a next step, I mean, to see how this can be used for virtual threads. Yes. Thank you for the mention.
Still have time for more questions? I have a question. Do you have a sense for how close to optimal your technique does, or is there any way to measure that, like what the optimal decisions would be in hindsight?
Well, the optimal decision, yes, well, because this finding the optimal using a model, it's not very easy because in different infrastructure that you run, you might change. You don't know the device, you don't know the CPU cores that you have. So having a model that you can use predefined weights for the GC and the I/O, it's not so easy. So we use the sum of this cost in order to know that, in order to not use weights. Now for the optimal, to find the optimal, it's not very obvious which is the optimal in each runs and how you are going to find it.
Mm.
Yeah.
We still have time? One thing, this is more of a clarification question, but I didn't fully understand how, like, the number of mutator threads is relevant. Are you adjusting the number of mutator threads, or how does that come into play?
Well, the number of mutator threads can be increased, decreased during execution based on the application, because it might create some threads, then stop these threads and create some others. Because we are inside the runtime, we know when the application creates a new thread, and we count it and we use it to monitor it in the eBPF.
Nice. Last chance. All right, thanks.
Thank you very much.